Thanks for watching Hariverse explore the secrets of 3-Eye Atlas. If you enjoyed this kind of calm, mysterious deep dive into space science, please like the video, subscribe to Hariverse, and share it with a friend who loves cosmic mysteries. Your support helps keep these investigations going. The sun is in a restless mood. Its surface roils with magnetic knots and bright scars that mark the sites of recent eruptions. And space around it is thick with charged particles that stream outward in great, curling clouds. Astronomers call this phase a solar maximum, the crest of an 11-year cycle when the star grows more active, more unpredictable, and more generous with energy than usual. It began in October of the year 2024, and by the time the following year unfolds, the peak has passed, but the aftershocks remain. High above Earth, particles from recent outbursts sweep along invisible lines of the planet's magnetic field and pour down toward the poles, where they light the upper atmosphere in curtains and arcs of color. For months, people far from the usual auroral zones have been walking out under the night sky and finding it subtly changed, washed with greens and purples that rarely appear so bright or so far south. A solar maximum does this. It turns the space around Earth into weather. And that weather is now close to its most turbulent state, when a new object enters the story. Far beyond the orbit of Mars, an icy speck crosses an imaginary boundary that marks the start of the inner solar system. It is small against the darkness, smaller than a single pixel in many telescopes, and yet its trajectory already stands out. The object is moving too fast to be bound to the sun in any ordinary way. When scientists trace its path backward on their models, the orbit does not curve neatly around the star like a long, slow ellipse. It comes in on a near straight track from interstellar space. This makes it only the third known visitor of its kind, an object that does not belong to the family of planets, moons, comets, and asteroids that formed with the sun. The official designation that appears in early circulars is technical and coded, but for the purposes of this story, the object is called 3-Eye Atlas. The name hints at its origin. The first part marks it as the third known interstellar object. The second part recalls the survey project that first reported it as a faint moving point among the background stars. At first, 3-Eye Atlas looks like a comet in the most general sense, a nucleus hidden inside a cloud of gas and dust that astronomers call the coma. Many comets behave in this way. They spend most of their lives in the deep cold beyond the planets, then drift inward until sunlight begins to heat their surfaces. Ices in the upper layers turn directly into gas, dragging loose dust with them and forming a glowing envelope around the solid core. With time and continued heating, sunlight and the flow of charged particles push the coma backward and shape it into a tail. In broad outline, 3-Eye Atlas fits this pattern, but the details do not. From the first months of observation, its brightness is oddly steady. Comets usually flicker and wobble as jets of gas turn on and off across their surfaces, and as their rotation presents different faces to the sun. But this object seems to glide inward on a remarkably stable light curve. Its path through space is similarly clean. As far as tracking data can tell, 3-Eye Atlas follows a straight prediction, hardly nudged by any faint jets of gas that might disturb its course. For a while, that lack of behavior is an anomaly in itself. A comet that refuses to act like a comet becomes a blank page, stubbornly unreadable. The timing of its arrival only deepens the sense that something unusual is happening. To have a large interstellar body pass so close to the sun exactly as the star rises to a once-in-11 years maximum of activity is statistically unlikely. The solar maximum means that the environment 3-Eye Atlas is about to cross is not gentle. It is filled with bursts of radiation, floods of particles, and gusts of solar wind that expand and contract with each eruption on the star's surface. When a solar flare erupts, it bathes nearby space in high-energy light. When a coronal mass ejection occurs, a portion of the outer solar atmosphere is lifted and blown outward, a wave of plasma that can sweep across planetary orbits. Some of these waves reach Earth and rattle the planet's magnetic field, generating the auroras that have become familiar headlines. Others pass harmlessly into the wider system. All of them travel along the same road that 3-Eye Atlas is now walking. From a scientific point of view, this coincidence is a gift. A comet, or comet-like body, plunging through the most active phase of the sun's cycle, offers a natural laboratory for how icy interstellar material behaves under intense stress. The same particles that color the auroras also strike the coma of the visitor, strip electrons from atoms, and set up faint, glowing emissions that can be analyzed by spectrographs. Each color, Each spectral line encodes information on the chemistry of the gas and the state of its atoms and molecules. If 3I Atlas is a normal comet from another star, its coma might betray traces of alien chemistry. Ratios of common elements like carbon and nitrogen could differ subtly from those in local comets. Rare molecules could appear or vanish. The pattern would help reconstruct the environment in which it formed, perhaps long ago around a distant young star. If it is not normal, these same observations might be the first hints of that difference. Yet the same alignment of circumstances that makes the object scientifically valuable also makes it frustrating to see. When 3I Atlas approaches the point in its orbit where it will be closest to the Sun, the geometry of the solar system places Earth on the far side of the star. From the ground, the visitor is lost in glare. Even space telescopes near Earth, such as the Hubble Space Telescope or the James Webb Space Telescope, cannot safely look so close to the blinding disk. Direct imaging from the home planet's neighborhood has to pause, just as the encounter becomes most dramatic. To fill the gap, scientists turn to eyes placed elsewhere. One key asset is a spacecraft orbiting Mars, equipped with a sensitive camera that can track faint objects against space. As 3I Atlas sweeps through the Martian neighborhood on its inward fall, this orbiter captures a sequence of images from a vantage point no other mission shares. Later, image processing extracts a single frame that shows the object at the smallest apparent size it will ever have in any camera. This is the highest resolution picture that will ever be taken of 3I Atlas. It is anticipated with quiet hope. When the processed image is finally examined, what appears is a single bright fuzz, a compact white blur with no visible structure, no obvious jets, and no hint of a solid shape embedded within. The halo stretches only enough to prove that gas surrounds a core of some kind, but the core itself remains hidden. For all the care and planning that went into that closest view, the mystery remains unresolved. The most detailed picture yet taken of an interstellar visitor tells almost nothing about what it looks like. The object continues inward, leaving behind data that is informative in some ways and stubbornly blank in others. Around it, the solar maximum continues as well, flares rising and falling from the sun's surface, coronal mass ejections rolling outward in great arcs, auroras rippling through Earth's night skies. In this restless environment, 3I Atlas approaches its perihelion, the moment when it will be nearest to the star. So far, it has held its secrets close. That is about to change. Long before 3I Atlas brushes past the sun at close range, the effort to understand it has already begun to test the limits of available instruments. When it is first picked up by wide-field surveys, the object is little more than a faint, moving mark that shifts its position night after night against the relatively fixed background of stars. Automated software flags it as interesting because its track does not fit the usual patterns of asteroids or long-period comets bound to the sun. Follow-up observations from larger telescopes refine the orbital solution and gradually confirm that this is an interstellar path, a trajectory that begins far outside the sun's sphere of influence. With this realization, observatories around the world adjust their schedules. They start inserting brief exposures of the new object into nights that were already accounted for, and they start watching for small changes in brightness and color that might reveal something about its nature. At the distances involved, the nucleus of 3I Atlas is far too small to resolve. The only thing telescopes can record is the combined glow of the coma and any very early tail. In those first months, as the object lies between the orbits of Jupiter and Mars, the light it reflects is dominated by longer wavelengths, skewed toward the red end of the spectrum. That in itself seems unremarkable. Many comets show a reddish tint when they are far from the sun because sunlight is scattering through dust grains and passing through gas made of familiar molecules. The pattern suggests that 3I Atlas is, at least in these early stages, behaving like a cloud of ordinary comet material. Spectrographs that split the light into its component colors confirm broad features consistent with gas and dust. There is no sharp signature that would immediately mark it as exotic. Yet, researchers tracking its light curve notice that the object is strangely well behaved. The brightness creeps upward as it drifts sunward, but it does so with a smoothness that is not typical of comets, which often show irregular jumps when a new patch of ice on their surface is exposed to the sun, or when a fresh jet of gas erupts from a fracture. The path of 3I Atlas through space is equally smooth. Small forces from escaping gas usually give comets a drift, but the early tracking data show almost no deviation from the path predicted by gravity alone. Computers are set up to test for hidden motions. to search for any difference between the calculated orbit and the observed positions on the sky. Run after run returns the same basic answer. If non-gravitational forces are acting, they are so gentle that current measurements cannot pick them out. The object seems to be coasting. This is not easy to interpret. The lack of early activity might simply mean that the outer layers of the nucleus are unusually tough, or that volatile materials are buried deeper than usual. Some researchers suggest that the surface could be crusted over with a traveled skin, hardened by previous passages close to other stars. Others argue for a more mundane explanation. The instruments are seeing only an average, and small irregularities are being washed out by distance and limited resolution. Still, the sense grows that 3I Atlas is conserving itself for a more dramatic phase closer to the Sun. That phase begins as the object approaches the orbit of Mars. From this vantage point, spacecraft that already circle the red planet can turn their cameras toward the visitor. One orbiter, carrying a high-resolution imager originally designed to examine the Martian surface, is tasked with capturing 3I Atlas at the moment of its closest approach to Mars. This geometry will never repeat. No planet will ever again be so near to the object. Engineers adjust pointing routines and exposure times, using careful calculations to track a tiny, fast-moving target against a star field. When the data return, the team extracts a single, sharp frame where the object is centered and relatively bright. This is the image that, on paper, holds the greatest promise of revealing structure. Yet, when the frame is processed and enhanced, 3I Atlas remains stubbornly featureless. The small disk of light is not quite a point, which proves that a hazy coma surrounds some kind of solid core. But there are no visible jets, no irregular edges, no hint of a resolved shape. It appears as a tight, symmetric glow. The image is scientifically useful because it places an upper limit on the size of the nucleus. Since nothing larger than a certain scale can be hidden within that blur, theorists can constrain the range of possible diameters. Even on the more generous estimate, the solid body is measured in only a few to perhaps a dozen kilometers across. That makes it large for an interstellar fragment, but still small compared to planets or moons. The picture also confirms that the coma at this stage is compact, not yet stretched out into a tail. In terms of appearance, however, it is frustrating. For a brief period, humanity looked at an interstellar object from closer range than it will ever do again, and it still appeared as little more than a fuzzy point. After the Mars encounter, the geometry of the system turns against Earth-based observers. As 3I Atlas continues inward, it moves toward a position almost directly behind the Sun from the point of view of Earth. Ground-based telescopes and mini space telescopes cannot see it at all. From a scientific perspective, the moment is awkward. The most intense part of its encounter with the Sun, the section of the orbit called perihelion, when the distance between the object and the star is at its minimum, is also the moment when observers near Earth must look away. The line of sight to 3I Atlas runs too close to the solar disk. The glare would burn out detectors and scatter in telescope optics. To follow what happens next, astronomers rely on a different class of instrument: coronagraphs, telescopes designed explicitly to look at the regions around the Sun by blocking the blinding central light. A coronagraph uses a carefully shaped mask or disk inside the optical path to mimic an artificial eclipse. This disk is adjusted so that it covers the Sun's bright surface exactly, allowing the much fainter outer atmosphere, the corona, to come into view. Spacecraft, such as the Solar and Heliospheric Observatory, operated by the European Space Agency and NASA, and weather satellites that monitor the Sun for storm activity, carry coronagraphs that continuously image this tenuous halo. Their primary purpose is to watch for solar flares and coronal mass ejections, the great billows of plasma that erupt from the corona and blow outward through the solar system. As a side effect, any comet or asteroid that passes close to the Sun can also be seen against this dim backdrop, provided it is bright enough. As the date of perihelion approaches, teams running these solar watching missions adjust their analysis pipelines. They instruct software to highlight moving points that diverge from the usual solar structures. Soon, 3I Atlas appears in the frames as a shifting speck against the ghostly halo of the corona. Over a span of days, that speck does not simply drift. It climbs in brightness at a rate that quickly attracts attention. Objects moving closer to the Sun always grow brighter to some degree. As they fall inward, they receive more light and re-radiate more energy. Dust and gas released by heating also expand the size of the coma, increasing the scatter of sunlight. What stands out in this case is the scale and speed of the change. In only a few days, the apparent brightness of 3I Atlas increases by a factor that is estimated at several hundred times its earlier level. This is not a gentle rise, it is an abrupt and pronounced surge. For comparison, standard comet behavior under similar conditions might see an increase of 10 to perhaps 100 times in brightness, depending on composition and how close the object passes. Here, the jump appears to reach roughly 400 times. Energy from the solar maximum is pouring into the object, and something inside is responding vigorously. The coronagraph images show the point of light swelling and hardening until it dominates the small region of sky around it. Simultaneously, instruments that can isolate different colors of light begin to record a shift in the spectrum. The glow of 3I Atlas is no longer dominated by the same red tones that marked its earlier journey. Subtle changes in the balance of wavelengths hint that the emission is moving towards shorter, more energetic colors. At first, the change is partial, a complication added to what was once a simple red-biased spectrum. Then, as perihelion proper begins, the entire profile appears to tip. To those who specialize in reading such graphs, the message is clear. The object is not only brighter, it is different. Under the combined pressure of sunlight, radiation, and charged particles from a stormy star, an interstellar visitor has started to behave in ways that stretch the usual language of comet physics. The simplest questions now become harder to answer. How much of the new light is reflected and how much is emitted by excited gas? Which atoms and molecules are responsible for the change in color? How much energy must be released from within that small nucleus to produce the observed surge? 3I Atlas, seen as a smooth and conservative traveler on its path inward, is now in open reaction with the environment around the Sun. The data streaming back from coronagraphs and other instruments show that the time of quiet approach is over. What happened next would move the object from merely interesting to deeply puzzling. As the surge in brightness takes hold, another change begins to write itself into the light of 3I Atlas, this time in color. During the slow approach through the outer solar system, the object presents a familiar character. The glow of its coma is dominated by longer wavelengths, shifted toward the red end of the spectrum. That kind of tint is common among comets. Dust grains suspended in gas scatter sunlight in a way that enhances redder light, and many of the molecules that make up a normal coma, such as simple carbon-containing compounds, emit more strongly in bands that blend into a reddish cast when viewed as a whole. Instruments that separate light into bands confirm this behavior early on. There is nothing in those first spectra that obviously marks 3I Atlas as an outsider, beyond the fact of its interstellar trajectory. Then, as weeks pass and the object crosses from the realm of Jupiter toward the orbit of Mars, a subtle drift appears in the data. The balance of colors begins to shift. Ratios of intensity in certain bands climb and others fall, and the overall impression of the coma moves toward the middle of the visible range. By late northern summer, the glow appears centered on green rather than red. To a casual observer, this might sound like a minor detail, but to the teams who watch these traces day after day, it is a surprise that lands with quiet weight. Green comas are not unknown. Some molecules, when broken apart by sunlight, can emit strongly in this region. In particular, small carbon chains in a gas can create a characteristic green emission when their bonds are excited and then relax. Many comets briefly display such colors near their inner regions. The difference here is the timing and the scale. In 3I Atlas, the green phase arrives while the object is still relatively far from the Sun, at distances where the energy available for driving such emissions is usually more modest. The transition is also orderly. Rather than showing a mix of red and green in some complicated blend, the spectrum slides in a way that suggests a systematic change in the gas. Something about the composition of the coma is evolving, or the distribution of that material around the nucleus is being rearranged. Scientists propose cautious explanations. One possibility is that different layers within the nucleus are beginning to contribute gas at different stages of heating. As the Sun warms the surface, more volatile ices buried under a crust might begin to sublimate, releasing molecules that were not present in large quantities before. Another suggestion is that solar radiation is altering existing gas, breaking molecules into fragments that have different emission properties. In both cases, the change is framed as a natural outcome of complex chemistry on and around a small body that is experiencing a changing environment. Yet the timing still feels off. Models that attempt to reproduce the observed shift often require either unusually high concentrations of certain species or an unusually clean transition between them, as if the nucleus were layered in distinct shells of material that activate one after another. As perihelion draws nearer and the object enters the domain where coronagraphs and other sun-watching instruments can see it, a second and more dramatic color shift takes place. The green phase does not deepen into yellow and then red, as might be expected if dust and complex organic compounds begin to dominate the scattering of sunlight close to the star. Instead, as the brightness surge builds, the spectral curve tilts further towards shorter wavelengths. Emissions begin to peak in the region associated with blue. High-energy processes are now driving the visible signature of the coma. In simple terms, 3I Atlas has become blue, not in a poetic sense, but as a measured fact. This is not what standard comet physics would predict. Close to the sun, heating becomes intense. Dust production tends to increase, and scattering by that dust often reddens the light. Some gas emissions also brighten, but the overall blend normally moves toward warmer tones. To get a net shift from red to green to blue requires either an unusual dominance of specific high-energy emission lines or a configuration in which ordinary red and green contributions are suppressed. The list of candidate mechanisms is short and strange. One idea is that a previously dormant reservoir of gas suddenly vents from within the nucleus as fractures open under thermal stress. If that gas is rich in species that fluoresce strongly in blue under ultraviolet radiation, the spectrum could tilt in this direction. However, at present there is no well-established example of a comet releasing a volume of purely blue favoring gas on the scale required to account for the observed change. Another possibility put forward is that the color shift is a byproduct of a breakup event. If the nucleus is cracking apart, exposing fresh material and sending clouds of debris into the coma, the scattering properties of the dust could change. Very fine particles interact with light differently than larger grains and could, under certain narrow conditions, alter the color balance toward blue. This would require a particular size distribution and composition of dust, and it would usually be accompanied by obvious signs of disruption, such as a swarm of fragments or a rapidly expanding cloud. Observers look for these telltale signatures in the coronagraph data and in whatever supporting images exist. They do not find clear evidence of a shattered nucleus. As far as the available resolution allows, 3I Atlas remains a single object. Its inner glow, though bright and transformed, does not show multiple cores. It has survived perihelion intact, at least at the scales that can be seen. With the breakup hypothesis weakened, attention returns to the question of chemistry and internal activity. The fact that the most intense color change coincides with the most intense phase of solar exposure suggests that energy is being absorbed and re-emitted by material very near the surface, or just beneath it. The corona around the sun during this solar maximum period is full of high-energy photons and charged particles. Some of these penetrate the coma and reach the nucleus, where they can alter bonds, create radicals, and trigger cascades of reactions. If 3I Atlas contains compounds that are rare in local comets, perhaps formed in a different kind of protoplanetary disk around another star, the pathways those reactions take could be unfamiliar. The blue flare may be the outward symptom of an internal chemistry that does not align neatly with existing models. The key point is that the change in color is not gradual and not fully accounted for by distance to the sun alone. It is as if a switch has been thrown at a particular threshold of heating or irradiation, turning on a new mode of emission. The brightness jump and the shift in spectrum reinforce each other. Both tell a story in which the object is no longer simply reflecting light. It is, in some sense, powered from within. For some researchers, this remains comfortably within the bounds of natural physics. An exotic but still natural composition can explain a great many odd behaviors. Comets are messy mixtures of ice, rock, dust, and organic material, and the range of possible outcomes under extreme conditions is broad. For others, the pattern of events is beginning to resemble something less random. A color that changes in a sequence opposite to what is expected, at a critical distance from the sun, in synchrony with a dramatic energy release, starts to look like a response. At this stage, such thoughts are only that. Thoughts, noted perhaps in private discussions rather than official reports. The language in public analyses remains careful, full of conditional phrases and alternative scenarios. Still, even in cautious prose, a new sense of unease appears between the lines. This is the moment when 3I Atlas crosses a line in collective perception. It ceases to be a quiet, conservative traveler and becomes a dynamic system undergoing a transformation. The sun, in its active phase, has pressed hard on the visitor, and the visitor has answered in a way that does not fully match expectations. The story of color that began with an ordinary red haze has become, by the time of perihelion, a blue beacon. That beacon, in turn, illuminates something else, something not directly visible but traced in motion. The first signs that gravity alone no longer guides the path of this interstellar body. At perihelion, 3I Atlas enters a region of space where conditions are shaped by the most intense output of the sun. The distance between the object and the star reaches its minimum, and the environment is crowded with energy. The solar maximum ensures that this is not an ordinary passage. The corona is bright and extended, threaded with loops of magnetized plasma that rise and fall. Coronal mass ejections lift portions of this outer atmosphere and send them outward as expanding shells. High-energy photons bathe everything nearby, and streams of charged particles rush along the paths laid down by tangled magnetic fields. Any small body that crosses this zone is exposed to radiation, heat, and the mechanical push of solar wind at levels far above the background. In that setting, the behavior of 3I Atlas comes under close scrutiny. The coronagraphs that have tracked its approach now record a sequence of frames in which the point of light representing the interstellar visitor swells and hardens into something more substantial. The earlier rise in brightness steepens. Within a span of days, the measured intensity increases by a factor of several hundred relative to values recorded only a short time before. This is not merely the effect of decreased distance. The scaling with proximity is well understood, and models can predict how bright a standard comet should appear at each stage of its orbit. 3I Atlas exceeds those predictions by a wide margin. The sudden blue-dominated emission observed in spectra indicates that gas in the coma is being excited in a way that requires significant energy input. At the same time, the overall luminosity suggests that a very large volume of material is involved. The combination implies that the nucleus is no longer just a passive reflector of sunlight and emitter of gently warmed gas. It is undergoing a major outburst. In many comets, perihelion is accompanied by such episodes. Crusts fracture, pockets of volatile ice are exposed, and jets of gas and dust erupt from specific regions. These jets can be irregular and short-lived, creating fluctuations in brightness and subtle shifts in the centroid of the coma. Usually, these effects are superimposed on motions that still closely follow the curve dictated by gravity. The path bends around the sun in a predictable way, and any deviations are small corrections. With 3I Atlas, analysts begin to notice that the residuals between predicted and observed positions are growing in a particular pattern. When they fit a purely gravitational orbit using data from before perihelion and extrapolate forward, the actual positions of the object in coronagraph images start to drift away from that path. The change is not chaotic. It has direction. The object seems to be moving slightly away from the sun, compared with where it ought to be if gravity were the only force acting. At first, the difference is subtle, comparable to the uncertainties in measurement. Teams hesitate to draw strong conclusions. Coronagraph data are not primarily intended for precise astrometry. The bright, structured corona provides a complicated background, and the artificial eclipse mask can introduce distortions. Yet, as more frames accumulate, the case grows stronger. Time series analysis shows a consistent trend. 3I Atlas is being pushed. The term used to describe any such motion is non-gravitational acceleration. In the context of small bodies, this phrase usually refers to the recoil caused by gas escaping from the surface. When a jet of gas flows away from a nucleus, it exerts a small thrust in the opposite direction. If the behavior of the jet is steady over some interval, the result can be approximated as a gentle, continuous acceleration. For most comets, this effect is modest. The resulting deviations in the orbit are measurable but do not dominate the dynamics. Observers characterize such cases by introducing additional parameters into their orbital models, terms that capture the average push in radial and transverse directions relative to the sun. When the same approach is applied to 3I Atlas using the perihelion data, the values required to match the observed positions are larger than expected. The acceleration component pointing away from the sun stands out. On the day when the object passes through its closest point to the star, the inferred change in its position relative to a purely gravitational path is estimated to be on the order of a couple of hundred kilometers over the span of a day. with roughly 135 kilometers of that shift corresponding to a sideways deflection away from the solar direction, and around 60 kilometers accounting for a change in speed relative to the Sun. The combined magnitude of this non-gravitational acceleration is therefore in the range of 200 kilometers of effective displacement per day. To place that in context, scientists compare it with other known objects. One reference case is another interstellar visitor, a body that passed through the solar system several years earlier and that exhibited modest non-gravitational accelerations as it warmed. In that case, typical deviations attributable to outgassing were estimated to be around 100 kilometers per day at most. 3I Atlas appears to be experiencing roughly twice that. When the comparison shifts to a large, energetic comet native to the solar system, one known for its strong outgassing and bright display during its passage through the inner regions, the difference becomes even more striking. In that well-studied example, the non-gravitational terms corresponded to displacements of only a small fraction of what is now being inferred for 3I Atlas, perhaps 1% of the current value. In other words, the amount by which the interstellar object is being pushed by forces other than gravity is unprecedented in the existing sample. What makes this more intriguing is that prior to perihelion, the same object showed almost no sign of such behavior. Through months of approach, the trajectory remained close to purely gravitational. The coma was stable and symmetrical, the light curve smooth. Only when 3I Atlas plunges into the intense radiation field of an active sun does this new regime begin. The non-gravitational acceleration turns on in synchrony with the blue brightening, and both phenomena reach their most extreme state near closest approach. One interpretation is that the surface of the nucleus contained layers of material that could only be activated once a certain threshold of energy was reached. Under this view, the solar maximum simply ensured that the necessary conditions were met. When the threshold is crossed, volatile gases trapped in deep pockets erupt, producing a powerful recoil. The fact that the direction of the acceleration is dominantly away from the Sun would align with jets emerging on the sunward side, blowing heated material outward and pushing the nucleus backward. In this scenario, 3I Atlas is still a comet, albeit one with an unusual internal structure and perhaps unusual composition. Another interpretation is more subtle. The direction of the acceleration is not perfectly radial. There is a transverse component that shifts the orbit in a way that resembles a deliberate change in course, a small but persistent steering effect. Natural jets are messy. They turn on and off, wander with rotation, and tend to produce complex, sometimes canceling contributions. The net force often averages out over a spin period. For an object that rotates in roughly 16 hours, as estimates suggest 3I Atlas does, any one fixed vent on the surface should sweep around and spread its influence. To maintain a coherent push in one direction over many rotations requires either a very specific geometry, a particular configuration of jets balanced around the spin axis, or some other organizing principle. Once this is realized, some researchers begin to frame the behavior differently. If there were a controlled source of thrust on or within the object, acting continuously in a preferred direction, the observed pattern would not look very different. A device that emits mass or energy in a collimated stream could, in principle, produce a steady non-gravitational acceleration aligned with a chosen vector. In that light, the numbers extracted from the orbital fits take on a new meaning. They describe not just an unusual comet under stress, but a system that, on a purely formal level, behaves like a driven body. Publicly, official documents still describe the phenomenon in neutral language. They speak of strong outgassing, of extreme non-gravitational terms, of an interstellar comet responding to solar heating in a way that stretches existing models. Privately, discussions widen. The idea that some fraction of interstellar objects might be fragments of technology has been raised before in the community, but rarely with direct observational hooks. Here, an object that is already unique in its timing and color now displays a level and pattern of self-acceleration that is hard to reconcile with familiar examples. There is no decisive evidence, no radio signals have been detected, no clear artificial structure has been resolved. Yet the behavior of the orbit itself has become a kind of signal, one that forces a re-examination of comfortable assumptions. In the end, the data do not answer the question they raise. They only frame it more sharply. 3I. Atlas, under the pressure of an active sun, has changed its brightness, its color, and now its path. The next phase in the sequence will reveal what the internal changes are doing to the gas and dust around the nucleus, and whether the shape of that material can clarify the source of the force now acting on this traveler from another star. In the days after perihelion, when 3I Atlas begins to emerge from the glare on the far side of the Sun, attention shifts from its path to the structure of the material it is shedding. The first clear post-encounter images arrive from instruments designed to see faint detail near the bright disk, and they show a configuration that is immediately striking. At the center of the frame sits the main condensation, a dense glow that marks the core of the coma. Measurements indicate that this inner halo extends roughly 500,000 kilometers in every direction from the nucleus, a sphere of dust and gas held together by the weak gravity of the core and the collective behavior of its particles. Around mini-comets, such a feature is expected. What is not expected here is what rises beyond it. From the bright heart of 3I Atlas, at least 7 distinct jets of material appear to be shooting into space. These jets are not vague smears. Within the limits of resolution, they are narrow and separated, each one tracing a different path outward from the inner halo. Most of them are oriented away from the Sun, roughly in the direction a normal tail would take under the push of solar wind and radiation pressure. But not all of them follow that rule. A couple of smaller jets point toward the Sun, cutting against the dominant flow. For observers used to the familiar geometry of comet tails, this is a puzzling sight. Under ordinary conditions, the gases and fine dust released from a comet's surface are rapidly shaped by forces that favor a single broad direction. The solar wind, a continuous stream of charged particles from the Sun, exerts a gentle but persistent pressure that sweeps light material away from the star. At the same time, sunlight itself pushes on dust grains, more strongly on smaller particles than on larger ones, further encouraging an overall outward plume. The result, in textbook cases, is a tail that stretches away from the Sun, sometimes with separate components for gas and dust, but generally aligned. The sight of multiple discrete jets, some of them directed back toward the star, runs against this pattern. On a spinning nucleus, jets that erupt from different locations can form a fan, but even so, the dominant shaping forces usually smear them into a broad, unified structure over time. In 3I Atlas, the jets hold their individual identities over distances that suggest they carry a great deal of momentum. The object's rotation period adds another layer to the puzzle. Estimates based on subtle brightness variations and the periodicity of small structures in earlier data place the spin at around 16 hours. That means that any fixed point on the surface completes a full turn in less than a day. If each jet originates in a local vent, it should sweep around as the nucleus spins, drawing a spiral pattern in the surrounding space. Instead, the observed jets look almost stationary in orientation, over the interval covered by the first set of images, as if they are being maintained in preferred directions despite the rotation. A simple way to reconcile this is to assume that the jets originate from regions near the spin axis. Material vented from such areas would describe a much narrower cone as the body turns, and projection effects could make them appear nearly straight. However, mapping this onto the apparent directions of the jets requires a specific alignment between the axis of rotation and the direction to the Sun, one that is possible, but not automatically likely. Another possibility is that the jets do indeed sweep, but their emission is so strong that it dominates the image along certain directions, even after smearing. In that case, the visible spikes would be the brightest segments of a more complex spiral sheet. Teams modeling the flow of gas attempt to simulate these conditions. They assign different vent locations and strengths, spin states, and heat distributions to virtual nuclei and let them evolve under solar forces. Some configurations can reproduce a pattern of roughly sunward and anti-sunward jets for brief intervals, especially when the object is in a highly active phase and internal pressure is venting through a limited number of fractures. Yet again, the parameter space is narrow. The observed 7-jet arrangement, with its combination of steady directions and mixed orientations relative to the Sun, demands careful tuning. While these calculations proceed, the real object does not wait. In images taken only a day after the first clear post-perihelion view, the scene has changed again. The multiple small jets have merged into what looks, at this resolution, like a single massive plume extending away from the inner halo. This structure has the character of a large tail, although its appearance differs from the usual long, gently fanning streak seen in mini-comets. It has a denser, more columnar look, the brightness concentrated along a central axis and fading outward, more reminiscent of a continuous outflow under high pressure than a leisurely stream of dust. Measurements of its length suggest that this main plume reaches to nearly 3 million kilometers from the nucleus, a scale that is remarkable given the short time between images. In less than 24 hours, the visible extent of the debris has grown from a system of jets attached to a compact halo to a vast structure spanning several times the Earth-Moon distance. The inference is that the rate at which material is leaving 3I Atlas is enormous. Such mass loss would usually threaten the integrity of the nucleus. When a comet vents too aggressively, pressure can fracture the body, leading to a breakup into smaller pieces. Observations of previous comets under stress show elongated clouds, multiple brightness peaks, or outright fragmentation as typical outcomes. With 3I Atlas, however, the core continues to appear as a single condensation. There is no clear sign of a swarm of fragments. Despite having thrown off multi-million-kilometer plumes of gas and dust, it remains cohesive. This suggests that the nucleus is both massive and structurally robust. Estimates of its diameter lean toward the higher end of the early range, perhaps closer to 10 kilometers across than 5. A larger, denser body can endure more vigorous outgassing without being torn apart, and the continued presence of a compact central glow after such an outburst supports this view. The new images also reveal another feature. If the bright, long plume is taken as the primary tail, then a fainter, shorter structure can be seen stretching in almost the opposite direction, toward the sun. This secondary feature, sometimes called an antitail or sunward extension, is not entirely unknown in comet studies. Under certain viewing geometries, dust lying along the orbital plane can appear to extend toward the sun from the observer's perspective, even though the particles themselves are physically located in the usual away-from-sun direction. Projection effects can create the illusion of a sunward tail. In the case of 3I Atlas, however, the interpretation is complicated by timing and context. A sun-facing emission was already one of the early anomalies noted in the months before perihelion, when the object was still between Mars and Jupiter. At that time, the energy input from the sun was much weaker, and the presence of any apparent sunward structure raised questions about the distribution of dust and the role of solar radiation. Now, close to the sun and still in the grip of a solar maximum, the object again displays a clear feature in the direction of the star. The shorter plume, estimated at around 1 million kilometers in length, points back along the track of the incoming solar radiation rather than away from it. Even allowing for projection and complex orbital geometry, the persistence of this configuration at such different distances suggests that the effect is not only a trick of perspective. The sunward feature may reflect a genuine component of the gas and dust flow that is being guided or confined in an unusual way. At this stage, the interplay between the observed morphology and the measured non-gravitational acceleration becomes important. The main plume carries mass away from the nucleus in a direction that broadly matches the derived thrust vector pushing the object. The existence of smaller or secondary jets, some of them oriented toward the sun, means that mass loss is occurring in multiple directions. If the net effect is still a strong push away from the star, then the distribution of vent strengths must be uneven. The largest contribution must come from regions whose outflow points opposite the acceleration. For a naturally fractured body, this is possible, but requires a specific pattern of active areas. For a controlled system, it would be an expected outcome of design. Scientists, wary of drawing such conclusions without stronger evidence, focus instead on what can be stated securely. 3I Atlas has, within a very short span of time, gone from a nearly jetless object with a compact coma to a highly active nucleus surrounded by structured emissions, multiple jets, and a rapidly developing tail and anti-tail system. The mass and resilience of the core allow it to remain intact despite losing enormous amounts of material. The directions of the observed plumes, when combined with the measured deviations in the orbit, imply a complex interaction between internal activity and external forces. The environment of the solar maximum supplies abundant energy and a strong solar wind that can sculpt the outflow. The internal state of the nucleus, shaped by its unknown history in another stellar system, determines how that energy is absorbed and re-emitted as gas and dust. Together, these factors generate a display that stretches the familiar patterns of comet behavior. For some, the scene is an extreme but still natural expression of physics, chemistry, and dynamics. For others, the symmetry of the early jet configuration, the persistence of sunward structures, and the efficient way in which the outflow translates into a coherent change in motion hint at something more organized. The images do not reveal machinery or architecture. They only show gas, dust, and light. Yet in the absence of resolved detail, the shape of those simple elements becomes the main clue to what 3I Atlas is doing, and perhaps to what it is. As the complex structures around 3I Atlas settle into their new configuration, analysts return to a question that has accompanied the object since its discovery, but now carries a different weight. How large and how strong must the nucleus be to survive everything it has just endured? The images taken after perihelion show a central condensation that remains compact despite the violent outbursts, and the sheer scale of the plumes indicates that a great deal of material is leaving the surface. To reconcile these facts, models of the nucleus are adjusted and run again. Early in its approach, before any detailed structures appear, the brightness and distance of 3I Atlas are used to produce simple size estimates. These depend on assumptions about how reflective the surface is. A darker surface requires a larger body to produce the same amount of reflected light. A brighter surface could be smaller. With reasonable values for a comet-like object, initial calculations suggest a diameter on the order of a few kilometers, perhaps around 5 kilometers across. This would make the nucleus respectable but not exceptional by solar system standards. As more data arrive, especially during the active phases near perihelion, this conservative estimate begins to look insufficient. The volume of gas and dust needed to build a halo hundreds of thousands of kilometers wide and to feed a plume millions of kilometers long in such a short time implies an underlying reservoir that is both deep and extensive. If 3I Atlas were near the lower end of the size range, sustained activity on this level would be more likely to shred it than to leave it intact. Observers see no clear evidence of such catastrophic breakup. Instead, the core persists as a single, coherent source of emission. The mass of the nucleus must therefore be large enough, and its internal structure cohesive enough, to withstand the stresses of its own venting. When the models are updated to reflect this requirement, the preferred diameter shifts upward. A figure closer to 10 kilometers across becomes more plausible. Such a body, depending on its density, could have a mass many times greater than that of smaller comets. This matters for how it responds to both internal pressure and external forces. A massive nucleus can lose material at a prodigious rate and still retain most of its bulk. It can sustain large jets without being spun apart. It can also carry its own gravity well, weak by planetary standards, but strong enough to shape the immediate environment of its coma. Comparing 3I Atlas with previous interstellar visitors makes the picture clearer. The first known interstellar object, a strangely elongated body that passed through the inner solar system years earlier, is inferred to be only a fraction of a kilometer to perhaps a kilometer or two in its longest dimension. It is a small, fragment-like traveler, more akin to a shard than a world. The second confirmed interstellar comet, Borisov, is larger, with estimates that place its nucleus in the range of a few kilometers. In this company, 3I Atlas stands apart. If the higher end of its size estimate is correct, it is perhaps 20 times larger than the first object and around 10 times larger than the second. It may be, by a wide margin, the most massive interstellar wanderer yet identified. The implications of this reach backward as well as outward. To be moving freely through the space between stars, an object must either be ejected from its home system by gravitational interactions or thrown loose by some other energetic process. Small fragments are easy to imagine in this role. Collisions between planetesimals, close encounters with giant planets, and the chaotic early stages of planetary system formation can fling many minor bodies into interstellar space. The smaller and lighter they are, the more easily they are deflected, and the less likely they are to collide with something else before escaping. A large body, 10 kilometers across or more, is a different proposition. Its cross-section, the area it presents as a target to the hazards around it, is much greater. Over billions of years, traveling through regions periodically filled with dust clouds, passing near other stars, and crossing the subtle currents of galactic tides, such an object has many opportunities to interact, to fragment, or to be ground down by impacts. For one to survive intact long enough to wander from its home system to the Sun, and to arrive here in a form that can generate the observed activity, requires that it either experience a relatively gentle history, or that it possesses unusual strength. Either way, it draws attention. Statistically, the appearance of such a body in the solar system at this particular moment seems unlikely. The number of interstellar objects that pass through is not yet well constrained, but early estimates suggest that while small fragments might be fairly common, large ones are rare. The first detections may hint at a much larger unseen population. Yet the odds of a massive, robust interstellar nucleus intersecting the narrow band of space in which Earth-based technology can notice and study it are still small. When the additional coincidence of timing is included, the improbability deepens. The current solar maximum is not unique in cosmic terms. The Sun has cycled through many such peaks over its lifetime. What is unique is the alignment between this particular maximum and the current stage of human observational capability. At this point in history, there are survey telescopes capable of scanning wide swaths of the sky nightly, space observatories operating in multiple wavelengths, and spacecraft scattered from the inner planets to the outer solar system, many of them equipped to monitor the Sun and its surroundings. Only in such a context can an object like 3I Atlas be discovered early, tracked, and then watched in detail as it passes through the harshest part of the solar environment. If the same body had arrived a century earlier, it might have been seen only as a bright comet near the Sun, its interstellar origin unnoticed. If it had arrived a century later, it might have been observed with even more powerful instruments. The fact that it appears now, when the network of eyes in space and on the ground is just sufficient to reveal its most dramatic anomalies, but not quite sufficient to resolve its core, gives the encounter an oddly poised character. For scientists, such coincidences are both intriguing and suspect. On the one hand, they may simply reflect observational bias. Perhaps large interstellar bodies are more common than current models say, and it is inevitable that one will eventually pass through during an active solar phase. On the other hand, the layered unlikeliness of the situation invites more speculative thinking. If 3I Atlas were a natural fragment, its long journey through the galaxy and its arrival during a solar maximum could be chalked up to chance, multiplied over immense scales of time and number. Chance, given enough opportunities, will produce rare alignments. Yet the idea that this particular object, with its unusual color changes, extreme non-gravitational acceleration, and unusually structured outflows, just happens to present itself under conditions ideal for testing those anomalies, pushes some researchers to ask whether a different kind of process might be at work. One subtle line of speculation considers the possibility that large interstellar bodies are more likely to be noticed when they are not entirely natural. If even a small fraction of wandering objects are artifacts or carriers of technology, their behavior could be tuned, deliberately or otherwise, to interact with bright, active stars in ways that draw attention. In this view, the solar maximum is not merely a hazardous environment, but a source of energy to be harvested. A close pass during peak activity would make sense for a device that relies on solar input. The strong outgassing, the blue brightening, and the significant non-gravitational acceleration could then be symptoms of an energy capture and propulsion cycle rather than simple sublimation. This remains far beyond what the data can prove. No observational signature yet demands such an explanation. Nevertheless, the combination of large size, remarkable resilience, and statistically awkward timing means that purely random narratives are harder to accept without question. Even those who prefer traditional cometary models are compelled to refine them. They must account for how such a large body can carry the internal structure needed to produce the observed behavior, how it can remain stable over long spans of interstellar time, and how the population of similar objects might be distributed in the galaxy. This leads to broader questions. If 3I Atlas is an unusually massive ice and rock body, perhaps formed in the outskirts of a distant planetary system and flung free by gravitational chaos, then how many such bodies exist? Are they common relics of planet formation, or rare survivors of extreme events? If, instead, it belongs to another class entirely, one that includes engineered or partially controlled objects, then the statistics of its arrival might encode information about intentions or patterns far beyond the current scope of astronomy. In both frames, natural and speculative, the object acts as a probe. It tests the limits of current theories and the flexibility of interpretation. Its sheer presence, large, active, and resistant to disruption, forces the solar system to reveal what it can about the flows of material and energy near the Sun. At the same time, it invites those watching to consider that the cosmos may contain structures and histories that do not fit comfortably inside prior expectations. 3. I Atlas, in its size and survival, demonstrates that interstellar space is not only filled with small debris, but can also transport substantial worlds between stars. Whether this particular world is only a relic of distant ice or something more remains an open question, and the answer, if it exists, is now entangled with the network of instruments that continue to watch it from all across the solar system. Across the solar system, instruments that were never specifically designed for this object now find themselves drawn into a shared task. 3I Atlas has moved from a faint curiosity to a central target, and the distributed network of observatories that normally divides its attention among many phenomena begins to converge, quietly, on this single interstellar visitor. Near Earth, ground-based telescopes with large mirrors and wide light-gathering power watch the object whenever geometry and safety allow. Some are perched on dry mountaintops, where thin air and steady winds grant clear views. Others are robotic survey instruments that scan the sky in repeated sweeps, catching 3i Atlas at different points in its track. They record its brightness in multiple color bands, building light curves and spectral snapshots that chart how the coma and tail respond over time. In space, the telescopes that orbit outside the atmosphere provide a complementary view. The Hubble Space Telescope, with its long history of comet imaging, contributes high-resolution optical data whenever the object is sufficiently far from the sun to observe without risking instrument damage. Infrared observatories, sensitive to the glow of warm dust and gas, probe wavelengths that the ground cannot access. They measure the heat signature of the coma and tail, offering clues about grain sizes, compositions, and the balance between reflected sunlight and intrinsic emission. These measurements give insight into how energy from the sun is being processed by the material surrounding the nucleus. Farther away, missions scattered across the inner solar system add their own pieces. Spacecraft in orbit around Mars, already used once to capture the closest image of the object, continue to monitor it as the geometry allows. Probes nearer to the sun, such as those tasked with studying the solar wind and magnetic field, detect subtle changes in the local plasma environment as tail material from 3i Atlas drifts through. Instruments aboard these missions can measure how charged particles are deflected, how densities vary, and whether any unusual signatures accompany the passage of interstellar gas and dust through solar plasma. In the outer regions, past the orbit of Jupiter, long-lived spacecraft that still report on the conditions of the distant solar wind log any anomalies that might be related to the visitor's extended tail, though at those distances, signals are faint and difficult to interpret. Around Earth, a ring of satellites designed for other purposes becomes part of the observational campaign. Weather satellites, normally occupied with monitoring clouds and storms in the atmosphere, carry cameras that can be turned outward for occasional sky imaging. Spacecraft tasked with studying Earth's magnetosphere record how it responds to both solar activity and any additional charged material from 3i Atlas that might pass through its influence. Radio observatories, both on the ground and in space, listen in relevant bands for natural emissions associated with the cometary coma. Some also conduct targeted scans, searching for narrowband signals or patterns that might suggest coherent transmission rather than random noise. So far, no clear artificial signals have been reported, but the act of listening itself becomes part of the broader watch, another way in which the system tests the hypothesis that this is more than an ordinary comet. Data from these mini nodes flow back to processing centers. In some cases, this means control rooms at national space agencies, where teams of specialists familiar with each instrument comb through the readings. In others, it means distributed efforts across universities and research institutes, where groups adopt specific aspects of the problem: the chemistry of the coma, the dynamics of the tail, the fine structure of a non-gravitational acceleration, the possible implications of the rainbow shift from red to green to blue. Each dataset is processed, calibrated, and compared with models. Each modeling effort, in turn, is constrained by the need to remain consistent with all the other lines of evidence. This is where the watchfulness of the solar system becomes more than a matter of simple observation. It becomes an exercise in coherence. An explanation that fits one facet of 3i Atlas often strains another. A chemical composition that could produce the observed blue emission near perihelion must also yield the earlier red and green phases at the right distances and intensities. An internal layering that could drive the sudden jets and massive plume must also account for the nucleus remaining intact. A distribution of vents that can generate the measured, non-gravitational acceleration must align with the observed shapes of the tail and antitail. As more information arrives, each simple story is tested and, more often than not, found incomplete. For example, some early models focus on the idea that a specific set of exotic ices, uncommon in local comets but not forbidden by chemistry, could dominate the composition of 3i Atlas. Under intense ultraviolet light near the sun, these ices could fragment into species that fluoresce in blue, explaining the color change. Simulations show that this is plausible if certain ratios of elements are assumed. However, when those same models are used to predict the infrared glow and the timing of outgassing, they fall short. The predicted heat signature does not match the observed data, and the evolution of the coma brightness is either too slow or too fast compared with reality. Other models concentrate on mechanical structure. They imagine a nucleus that is heavily fractured internally, crisscrossed by voids and tunnels that channel gas toward the surface in confined streams. Such architecture could, in theory, produce multiple jets that remain distinct over long distances. It could also promote strong non-gravitational acceleration if the vents are concentrated in specific regions. But when researchers apply these structures to a spinning body of the inferred size, they find that stresses during perihelion would likely fracture the nucleus unless it is composed of material far stronger than typical cometary dust and ice. This pushes the hypothetical composition toward dense rock, maybe even metal-rich phases, which in turn conflict with the necessary volatile content to drive the observed outgassing. The solar maximum itself adds complexity. In a quieter solar cycle, the behavior of 3I Atlas might have been easier to attribute purely to its own properties. Instead, the star's elevated activity means that the environment is more varied and more violent. Changes in solar wind pressure, bursts of high-energy radiation, and successive coronal mass ejections create a background that is anything but steady. Each of these external factors can nudge the coma, alter the tail, and affect the energy budget. Disentangling what is driven by internal processes from what is imposed by fluctuating solar conditions becomes a central challenge. Observers comb through records of solar events, correlating them with changes in the appearance and motion of the object. Sometimes clear links emerge, such as a flare followed by a modest brightening, or a shift in tail orientation after a documented mass ejection. Other times, changes in 3I Atlas arrive without obvious external triggers, reinforcing the impression that something inside the nucleus is dictating its own schedule. The global watch extends beyond professional circles. Amateur observers with access to moderate telescopes contribute timing and brightness measurements from locations around the world, helping to fill gaps in coverage. Their contributions, pooled and curated, allow finer sampling of how the object behaves as it moves across the sky. These records confirm the rapid changes in brightness near perihelion and capture minor fluctuations during quieter periods. In an era where data flows freely and quickly, images and light curves appear in near real time, allowing a broad community to track the evolving behavior of the interstellar visitor. Within this tapestry of observation, patterns begin to emerge that move the narrative in small, precise steps. One pattern is that 3I Atlas often responds to solar stimuli, but not always in the way expected of a comet. Another is that its internal episodes of activity, including the major outburst near perihelion, seem to occur at thresholds of energy input rather than at regular intervals or in direct lockstep with particular solar events. The watching network also confirms that after the most intense phase, some of the unusual features persist longer than models predict. The sunward plume does not vanish immediately once the object has moved away from the very closest point, and the non-gravitational acceleration does not drop to negligible levels right away. Instead, it decays along a curve that hints at ongoing, controlled release of gas, rather than a simple exhaustion of surface ices. For astronomers and planetary scientists, this unfolding record is both exhilarating and unsettling. Each new observation constrains the space of acceptable natural models, closing off some possibilities and highlighting others. At the same time, the accumulating anomalies invite cautious forays into more speculative territory. Workshops and conferences hastily add sessions devoted to interstellar objects and to 3I Atlas in particular. Papers and preprints circulate that explore themes from unusual chemistry to hypothetical sail-like geometries embedded in the nucleus. Through it all, the tone remains mostly measured. The scientific habit favors conservative explanations and demands strong evidence before adopting extraordinary claims. Yet the very need to coordinate so many instruments and disciplines around a single, small point of light speaks to how strongly this object has captured attention. 3I Atlas, through the watchfulness it provokes, is quietly reshaping how the solar system is used as an observatory. Missions originally built to study the sun, planets, and the near-Earth environment are now being repurposed, at least in part, to probe an interstellar traveler. The response is not a planned campaign, but an emergent behavior of a network that has become dense and flexible enough to pivot when something unexpected appears. It is within this context of heightened vigilance that the next phase approaches, when the object will no longer be hidden near the sun from Earth's direct gaze, but will instead sweep past the planet at a distance close enough for every major instrument to lock on and study it in what may be the clearest view humanity will ever have. As 3I Atlas moves out from behind the sun and along its outbound path, its trajectory brings it toward a point in space where it will pass relatively near to Earth. The geometry is not one of collision, nor even of close approach in planetary terms, but in the scale of interstellar travel, it is a notable convergence. On the 19th of December, the distance between the object and the planet will reach a minimum, and for a brief window, the interstellar visitor will be as accessible to direct observation as it will ever be. This prospect shapes the planning of observatories months in advance. Schedules that are usually fixed long ahead of time are quietly adjusted. Blocks of observing nights are reserved. Radar facilities that can send powerful beams into space prepare their transmitters and receivers. The goal is simple in principle, but demanding in practice: to use every available tool to extract as much information as possible from this one opportunity. As the date approaches, the behavior of 3I Atlas continues to evolve. The intense activity of perihelion begins to moderate. The huge plume that once stretched millions of kilometers from the nucleus thins and elongates further as material is left behind along the orbit. The sunward feature weakens but does not vanish, lingering as a faint trace of the earlier antitail. The non-gravitational acceleration that so strongly affected the orbit near the closest point to the Sun begins to decline. Yet, calculations show that it remains measurable. The object is still being pushed in subtle ways that cannot be attributed to gravity alone, though the magnitude of the effect is now smaller. This decay pattern suggests that whatever internal processes drove the perihelion outburst are winding down along a curve rather than shutting off abruptly. By the time 3I Atlas draws level with Earth's orbit, the heliocentric distance has increased and the immediate solar environment is less severe, but the imprint of the earlier episode remains encoded in the state of the nucleus and surrounding coma. On Earth, the atmosphere and the rotation of the planet impose limits on what can be seen from any single location. To overcome this, observatories across different longitudes coordinate their efforts. As the object rises and sets over different continents, telescopes hand off the target from one to another, creating a chain of coverage that follows it across the sky. Large optical telescopes with adaptive optics systems, capable of partially correcting for the blurring effects of turbulence, attempt to resolve the inner coma at the highest possible angular resolution. They search for any sign of structure in the core, a flattened region, an elongated brightness profile, or hints of multiple peaks that might betray fragments or extended features. At the same time, spectrographs attached to these telescopes record the light in fine detail. They measure the depths and shapes of absorption and emission lines across optical and near-infrared wavelengths, tracing the composition and temperature of gases and dust. Differences between the inner and outer coma can reveal how material is being transported outward. Any unusual ratios of known molecules or the presence of unexpected species might provide further evidence that the chemistry of this object differs from standard cometary compositions. Space-based observatories add an important dimension. Freed from atmospheric disturbance and able to observe at wavelengths absorbed by air, they provide cleaner, more stable data. Infrared instruments focus on the heat of the nucleus in nearby dust. By modeling the way this thermal emission varies with viewing angle and time, researchers attempt to constrain the shape and rotation state of the core. Polarimetric measurements, which analyze the orientation of the electric field in the reflected light, probe the texture and size distribution of dust grains. These techniques, used on many previous comets, now confront a body whose interstellar origin and prior history may have produced different surface properties. Radar facilities, in particular those equipped for planetary defense work, play a special role. They transmit powerful bursts of radio waves timed to intersect the path of 3I Atlas, and then listen for echoes. The strength and spread of these echoes can, in principle, reveal the size, shape, and surface roughness of the nucleus with a precision unattainable in optical images. Radar has been used to map near-Earth asteroids in remarkable detail, returning silhouettes and even surface features. Applying the same method to an interstellar comet is technically challenging, because the distance is still great and the target is relatively small and moving quickly. But the potential return is significant. If the echoes are strong enough, they could finally distinguish between a roughly spherical lump of ice and rock and a more complex geometry. When the first radar returns are processed, the results are mixed. Signals are detected, but they are weak and noisy, at the threshold of what the systems can reliably interpret. Still, from these faint echoes, a few constraints can be drawn. The nucleus appears to be compact, without large, detached fragments nearby. Its overall radar cross-section is consistent with a solid body of several kilometers in diameter, lending support to the higher mass estimates derived earlier from activity models. However, finer details remain hidden. If there are subtle protrusions, concavities, or embedded structures, they are below the resolving power of the available data. In radio bands used for communication searches, dedicated campaigns scan the region of sky around 3I Atlas during the close pass. Arrays such as the Very Large Array and other radio telescopes listen for narrowband signals that might indicate intentional transmission. These efforts involve careful filtering of terrestrial interference and known astrophysical sources. The expectation, grounded in experience, is that nothing artificial will be found, and initial analyses support that expectation. No convincingly non-natural signals emerge from the noise. Yet the sensitivity limits of the instruments mean that only transmissions above a certain power threshold would be detected at this distance. A quiet object, or one communicating in forms not tuned to human instruments, would remain invisible. In the visible range, amateur astronomers join the watch. From dark sites under clear winter skies, small telescopes trace the motion of 3I Atlas against constellations familiar to casual stargazers. For many, it appears not as a spectacular naked-eye comet, but as a subtle smudge, a small, fuzzy star with a hint of tail, rendered more meaningful by the knowledge of what it is, rather than by its immediate appearance. Their images, stacked and processed, add to the record, capturing the evolution of the tail structure during the days before and after closest approach. These contributions confirm that the main tail continues to align broadly away from the sun, while the faint sunward feature gradually diminishes but does not entirely disappear. Through all this, the object's trajectory is tracked with increasing precision. Each optical and radar measurement refines the orbital solution, reducing uncertainties. The non-gravitational terms that describe the residual pushes beyond gravity are recalculated with better constraints. The picture that emerges is one in which the strong perihelion acceleration has begun to taper but remains non-zero even at the distance of Earth's orbit. 3I Atlas is still under its own subtle propulsion, whether through vigorous but diminishing natural outgassing or through some more controlled mechanism. Modelers attempt to reproduce this behavior by adjusting the distribution and strength of notional vents on the surface. Some succeed in generating a self-consistent set of parameters that roughly match both the observed jets and the orbital deviations. However, these models often require the vents to be arranged in ways that seem improbably coordinated for a random assemblage of fractures. They demand, for instance, that activity concentrates in regions that maintain a preferred orientation relative to the sun across many rotations, or that the temporal pattern of venting follows thresholds in solar input that mimic trigger points. None of this proves agency, but all of it keeps the question open. As the days around the 19th of December pass, data accumulates. Early hype gives way to the slower process of analysis. Preliminary images are processed, then reprocessed with improved calibrations. Spectra are stacked to increase signal. Artifacts are removed. Papers begin to circulate in which teams present their first interpretations. Some emphasize the ways in which 3I Atlas fits, however uneasily, within an expanded definition of a comet. They point out that outliers often appear when the sample size is small. Others highlight the persistent anomalies, the color sequence, the extreme non-gravitational acceleration, the antitail that resists simple projection explanations, and now the specific ways in which activity appears tied to solar thresholds. For a brief interval, the interstellar visitor is at the center of a focused, planet-wide experiment. Earth, wrapped in its auroral glow under the active sun, devotes a significant fraction of its astronomical machinery to watching a single, small body move past. Then, inevitably, the geometry begins to change. 3I Atlas moves on, its distance increasing, its apparent brightness fading. Practical constraints reassert themselves. Telescopes return to other projects. Spacecraft resume their primary missions. The visitor recedes, taking with it the possibility of any closer look. What remains is the archive. Terabytes of images, spectra, radar traces, plasma readings, and light curves, each a thin slice of information from a brief alignment in space and time. Within that archive may lie subtle patterns not yet recognized, correlations that will only emerge after months or years of careful work. For now, the immediate impression is paradoxical. The close pass has answered some questions about size, coherence, and broad composition, but it has not dissolved the deeper mystery. If anything, by confirming the robustness of the nucleus and the oddities of its behavior even at this distance, it has reinforced the sense that 3I Atlas is not easily categorized. The interstellar object has come near, allowed itself to be measured in more detail than any similar body before it, and then continued outward, leaving a trace of data and a set of questions that will outlast its brief time near the sun. With the close passage behind it, and the data streams now reduced to archived files, 3I Atlas begins to slip from the front pages of public attention. In the scientific community, however, the object moves into a different kind of spotlight. Freed from the urgent demands of scheduling and real-time coordination, researchers can now sit with the full record and ask a narrower but deeper question. Given everything that has been seen, what class of object can 3I Atlas reasonably belong to? The first and most conservative answer remains that it is a comet, albeit a comet that stretches the upper bounds of known behavior. In this framing, every anomaly is a point on a spectrum rather than a categorical break. The color transitions from red to green to blue become the signature of unusual chemistry in an interstellar mix of ices. The extreme non-gravitational acceleration becomes a case of exceptionally strong outgassing from a layered nucleus under the pressure of a solar maximum. The jets and plumes that defy simple geometry are expressions of a fractured interior venting through preferential pathways. The size and resilience of the nucleus, its ability to survive intense heating and massive mass loss without fragmenting, are consequences of an origin in a dense, perhaps metal-rich region of a protoplanetary disk. Simulation work can be made to support many of these points. By adjusting parameters for composition, layering, porosity, and spin, modelers can produce virtual objects whose behavior resembles the observed data in outline. One model might assume high concentrations of exotic carbon-bearing compounds that fluoresce blue under ultraviolet radiation. Another might invoke a crust of sintered dust, overlaying a volatile, rich interior, causing delayed but explosive outbursts once a critical depth of heating is reached. A third might propose an asymmetric internal structure that naturally channels jets into a pattern of multiple, persistent streams. None of these constructions is impossible. The universe is wide, and the sample of directly observed interstellar bodies remains tiny. It would be premature to assume that local comet physics covers all possible outcomes. Yet, as each model is tuned to fit one aspect of 3I Atlas, it tends to pull away from another. A composition that accounts for the color shift may fail to produce the observed mass loss rates without making the nucleus unreasonably fragile. A structure that can deliver the required non-gravitational acceleration may, under its own internal stresses, be prone to break up well before perihelion. When constraints from all datasets are applied simultaneously, the allowed space of purely natural explanations narrows. This does not mean it vanishes, but it becomes a carefully carved region rather than a broad field. In parallel with these efforts, a more speculative line of interpretation is explored with equal measures of caution and curiosity. It asks a different question. If 3I Atlas were not a purely natural object, how much of its behavior would need to be attributed to something like technology? The very phrase is slippery in an astronomical context. Technology, as understood on Earth, involves tools and systems built by biological intelligences under specific cultural and physical constraints. Extending that concept beyond the planet is fraught. Still, the definition can be broadened to include any structure or device whose properties are not easily explained as the product of simple gravitational and chemical processes. Under this expanded view, one possibility is that 3I Atlas is a hybrid. Its bulk could be that of an ordinary interstellar comet, but embedded within or attached to it could be components that respond actively to the environment. In such a scenario, the object would appear natural in many respects, including its rough shape and broad composition, yet exhibit behavioral signatures that arise from controlled systems. The sudden onset of strong non-gravitational acceleration near perihelion, aligned in a way that translates solar energy into a change of course, could be interpreted as the activation of a propulsion mechanism tuned to high radiation fields. The color shift to blue at the same time could reflect not only exotic chemistry, but also emission from ionized species used in such a system, analogous in a distant way to a thruster plume. The persistence of a sunward plume and antitail against both projection effects and solar wind pressure might then be seen as evidence that some fraction of the outflow is being directed or confined by electromagnetic means rather than simply blown back. Pushing this further, some thinkers entertain the idea of 3I Atlas as an artifact in a stronger sense, perhaps a dormant interstellar probe or a piece of a larger network of objects that travel between stars using gravitational assists and stellar energy to adjust their trajectories. In this view, the timing of the encounter with a solar maximum is not mere coincidence, but a consequence of a chosen path designed to maximize available power. A close pass during peak activity would offer abundant particle flux and radiation to drive whatever systems the object carries. The fact that the strongest anomalies appear precisely at this phase, and that they include both an intense energy release and a measurable thrust, is then read as circumstantial support. Even within this speculative frame, caution is necessary. There is, so far, no direct detection of artificial radio emission, no resolved images of regular structure, no signs of modulation or coding in the outflow that would compel a technological interpretation. The case, such as it is, rests entirely on the pattern and coherence of physical behavior. In the sciences, patterns invite hypotheses, but do not, by themselves, dictate conclusions. To avoid the trap of seeing intention in every anomaly, some researchers propose a middle ground. They suggest treating 3i Atlas as a test case for a broader category of objects that might blur the line between natural and engineered. Instead of committing to a particular narrative, they develop frameworks to classify behaviors: degree of deviation from gravitational motion, complexity of outgassing patterns, dependence of activity on external energy fields, and so on. In this taxonomy, 3i Atlas is not immediately labeled as an artifact. It is simply placed at the extreme end of several scales. It becomes a benchmark against which future interstellar visitors can be compared. If others arrive with similar suites of anomalies, the argument for a distinct class of objects, possibly including technological examples, would strengthen. If, instead, 3i Atlas remains an isolated outlier, the weight of probability would tilt back toward an unusual but still natural origin. Another axis of interpretation looks backward rather than forward. It considers what 3i Atlas means for the history of the solar system before its arrival. If large interstellar bodies like this are more common than previously believed, then the Sun and its planets may have been crossed by many such travelers over geological time, most of them unnoticed. Some might have passed too far away or too long ago to leave clear observational traces. Others might have plunged into the outer solar system without ever approaching near Earth. In that sense, 3i Atlas would be significant not because it is the first of its kind, but because it is the first encountered while a sufficiently capable network of instruments is in place. On the other hand, if its properties are indeed rare, then its appearance at a moment when that network exists becomes part of its story. A small subset of thinkers go one step further and speculate, quietly, about selection effects that are not purely observational. They ask whether it is possible that some phenomena in the galaxy are more likely to intersect with technologically active worlds, not through intention in any familiar sense, but through dynamics that favor such encounters. In these scenarios, stars with planets that emit certain signatures, perhaps in radio or light, could become statistically more likely to receive visits from interstellar objects on particular trajectories. The mechanics of such a process are not worked out in detail. The idea remains nebulous, a suggestion rather than a theory. It is mentioned here only because 3i Atlas, by its very presence and timing, has pushed open the window of imagination through which such questions can be posed without immediately being discarded. Throughout all of this, a thread of restraint runs through the scientific narrative. Working groups and review panels emphasize that extraordinary claims require extraordinary evidence, and that, at present, the data surrounding 3i Atlas, while rich and intriguing, do not cross that threshold. The anomalies are real and robust. The non-gravitational acceleration is measured. The color shifts and jet structures are documented. Yet none of these, alone or together, exclude every possible natural explanation. The safest working position is to treat the object as a rare and complex member of the comet family until and unless further evidence argues otherwise. Still, the experience of confronting these questions does something subtle to the way scientists think about the sky. It normalizes, if only slightly, the practice of considering technological interpretations alongside natural ones when confronted with unexplained patterns. It encourages the design of future surveys and missions with the flexibility to test for both. 3. iAtlas, regardless of its true nature, thus acts as a catalyst. It brings the possibility of interstellar technology into a more grounded, data-anchored conversation, not as a far-off speculation, but as one of several working hypotheses applied to a real object. As the analyses deepen and models become more sophisticated, the picture may sharpen in one direction or another. For now, the interstellar visitor occupies an ambiguous place in the taxonomy of things that move around the sun. Not a planet, not a simple comet, not clearly an artifact, but something that sits on the border between categories, forcing the map to be redrawn. Long after 3i Atlas has swung past the sun and crossed the plane of Earth's orbit, the object continues outward on its escape path. Its speed, set long ago in another system under another star, ensures that it will not be captured. The sun's gravity bends its trajectory, but cannot hold it. Each day, the interstellar visitor becomes fainter in the sky, not only because of distance, but because its outgassing is subsiding. The coma thins, the tail fragments into a diffuse trace along its orbit. Eventually, in ordinary telescopes, it will be indistinguishable from the dark between the stars. What remains, growing rather than fading, is the record of what it did while it was here. In data archives on Earth and in storage systems on spacecraft, the story of 3i Atlas is now distributed across thousands of files. Some contain direct images, coarse and fine. Others hold spectra mapped into tables, lists of intensity versus wavelength. Still others preserve time series of brightness, plasma densities, magnetic field readings, and radio noise. Each piece is a narrow window, but together they describe a coherent sequence of events: a quiet approach, an unexpected color evolution, a violent brightening near perihelion, a burst of non-gravitational motion, a phase of complex jets and plumes, and a controlled fading as the object departs. In the months following the close pass by Earth, analysis deepens. Teams that once focused on rapid reporting now turn to slower, more careful work. They correct instrumental biases, refine calibrations, and merge datasets from different instruments into unified products. Joint efforts emerge in which specialists in comet physics collaborate with experts in plasma interactions, radiative transfer, and orbital dynamics. Each group brings a different perspective to the same body of evidence. Some of the early tensions in interpretation soften as models improve. For instance, better treatments of how dust grains interact with intense solar radiation during a maximum help to explain certain variations in tail structure that first looked wholly anomalous. New laboratory experiments, where ices with plausible interstellar compositions are bombarded with ultraviolet light and charged particles, reveal complex emission patterns, including some that favor blue light under specific conditions. These results lend support to the idea that 3I Atlas could, in principle, be made of material that reacts in unfamiliar but still natural ways near the Sun. At the same time, not every anomaly yields so easily. The magnitude and timing of the non-gravitational acceleration, especially its sudden onset near perihelion after a long, quiet approach, remain stubborn features. Even with improved models of venting, it is difficult to reproduce the observed pattern without fine-tuning the distribution and timing of active regions on the nucleus.
The requirement that these vents combine to provide a coherent push in a particular direction over many rotations while the object spins in roughly 16 hours continues to narrow the range of acceptable natural scenarios. The persistent, structured sunward features in the coma, observed at multiple stages of the orbit and under different viewing geometries, also resist reduction to a single projection illusion. As a result, the classification of 3I Atlas does not settle into a simple category. Rather than being assigned firmly to the box labeled comet, it tends to sit in a margin between labels. Papers describe it as an interstellar object with comet-like activity that exhibits extreme non-gravitational forces and unusual spectral behavior. The language is descriptive rather than definitive. Terms such as candidate comet, active interstellar body, and outlier appear alongside more speculative phrases that are compartmentalized into discussion sections, where authors are free to consider broader implications without overstating certainty. Institutions that operate major observatories take note of this ambiguity. Planning documents for future survey telescopes begin to incorporate requirements aimed specifically at interstellar visitors. Detection algorithms are adjusted to flag not only objects on hyperbolic orbits, but also those whose light curves or colors depart from expected templates. Mission concepts, some already being discussed for fast response spacecraft that could intercept future interstellar objects, are revised to account for the lessons of 3I Atlas. Any probe designed to approach such a body now has to consider the possibility of extreme outgassing, complex jet fields, and sudden non-gravitational accelerations that could complicate navigation. At agencies such as NASA and the European Space Agency, internal studies explore what it would take to pre-position small, agile spacecraft that could be redirected on short notice when the next interstellar object is found. These concepts are still early, constrained by budgets and launch opportunities, but the experience of watching 3I Atlas from afar, while knowing that no mission could reach it in time, has left a clear imprint. The solar system, as a network of instruments, has proven that it can observe such an object. The next step, many argue, is to go and meet one. Within more speculative circles, the legacy of 3I Atlas flows along different lines. Researchers interested in the search for extraterrestrial technology incorporate the object into their frameworks as a case study. They refine criteria for what would count as evidence of engineered behavior in small bodies. They propose future observations that could be used to test those criteria more rigorously, such as high-cadence monitoring of light curves to search for non-random modulation, or carefully designed radio campaigns that remain sensitive over long periods as interstellar objects move through the solar system. 3I Atlas becomes, in effect, a reference point in discussions about how to recognize technology that does not declare itself with obvious signals. The general public's awareness, though dimmer than during the object's brightest phase, is not entirely lost. For many people, the idea that a body from another star system passed through the inner solar system during a time of heightened solar activity leaves a lasting impression.
The knowledge that this visitor may be larger and more massive than previous interstellar objects, that it behaved in ways that prompted serious scientific speculation about propulsion and internal energy sources, adds a layer of quiet fascination to what might otherwise have been a brief news item. In classrooms and popular science writing, 3I Atlas provides material for explaining not only comet behavior and solar cycles, but also how science responds to uncertainty. It shows that scientists can entertain multiple hypotheses, including those that touch on distant technology, without abandoning rigor. The object itself, untroubled by these interpretations, continues on. Beyond the orbits of the giant planets, where the solar wind is thin and the sun is a bright star rather than a dominant presence, its activity will eventually cease. The coma will collapse. Any remaining ices on or near the surface will refreeze. Dust will settle or drift away. The nucleus, perhaps scarred and reshaped by its encounter with a hot, stormy star, will return to a state closer to the deep cold it has known for most of its existence. It will carry with it whatever structural changes the solar maximum induced: new fractures, sealed vents, altered chemistry in its upper layers. After that, only the rarest of instruments, far from Earth, would ever be able to detect it as more than a point. In simulations that project its path forward, 3I Atlas leaves the sun behind and returns to the larger arena of the galaxy. It joins the diffuse traffic of interstellar debris and, perhaps, interstellar artifacts that drift between stars. Whether it will ever pass close to another planetary system in a way that allows its anomalies to be noticed again is not known. From the perspective of the solar system, its role has been to pass through once, under particular conditions, and to be seen. What that seeing has revealed is not a simple answer, but a structure of questions. How common are interstellar objects of this size and resilience? How often do they carry compositions or internal architectures that can produce the kind of behavior recorded here? To what extent can extreme but natural physics account for patterns that, at first glance, resemble controlled propulsion? How should future instruments be built and used so that the next such visitor, whether natural or not, can be studied in greater detail? None of these questions is resolved as 3I Atlas recedes. Instead, they settle into the background of scientific planning and curiosity, shaping the way new surveys are designed and how data from small, fast-moving objects is interpreted. The solar maximum that framed the encounter will ease and give way to quieter years. Auroras will fade back toward their usual ranges. The sun will enter another phase in its cycle. In time, other comets from the outer reaches of the solar system will fall inward, bright and photogenic, obeying familiar patterns. Against that familiar backdrop, the memory of an object that did not fit so easily will persist among those who studied it. 3I Atlas, whatever it is in detail, has altered the baseline. It has shown that the sky above is not only populated by bodies that belong to the sun, but can also be crossed by strangers that bring unexplained behaviors with them. The next time a faint, fast-moving point appears on survey images, with a path that leads in from the dark between the stars, the questions asked of it will be sharper, because this one came before. The mystery of 3I Atlas is not that it offered some final revelation, but that it refused to. It came, changed under pressure in ways that forced new thinking, allowed itself to be measured just enough to confound simple stories, and then left, carrying its remaining secrets away into interstellar night.